Yeah, in this video, I'm going to discuss about this VSEPR theory, the shape of the chlorine trifluoride molecule according to this VSEPR theory. In my previous video, I've well dealt with this VSEPR theory in detail. Now, in this video, I'm going to discuss about this chlorine trifluoride. Yes, chlorine trifluoride in detail about its equatorial positions and uh, yes, and so on. Yes, when we come to this chlorine trifluoride, this chlorine, we know that it is an seventh group element. So its atomic number is 17. So its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 6, 7, 8, 9, 10, and 3p5, right? So it is 2, 5. So electronic outermost electronic configuration is 7. That means the number of valence electrons is 7 in this case. So we know that this VSEPR theory is totally based on the number of the valence electrons or the number of the electrons in the outermost shell. So the name valence shell electron pair repulsions theory. So it's based on the repulsions in between the electrons which are present in the valence shell. That means repulsions in between the lone pairs and bond pairs of electrons. So the steric number is equal to this formula, this half into the number of valence electrons in the center atom. So number of valence electrons on the central atom plus the number of the bonds connected to it, and plus or minus the charge. If there is a negative charge on that particular molecule, just add it, and if there's a positive charge, just subtract it. So half into the number of valence electrons is 7 in this case. So chlorine is seventh group elements, the number of electrons, valence electrons is 7. So plus the number of the bonds is it's connected to 3 fluorine atoms. So number of the bonds is 3 and there is no charge on this. So it is 5 here. So the steric number is 5. So if the steric number is 5, what do you mean the hybridization is sp3d? So the structure will be trigonal bipyramidal. So there's a 5 bonds totally. So either it is lone pairs or bond pairs. Just look at it. We'll look at those in my next slides. The structure is trigonal bipyramidal. Bipyramidal structure. So yeah. And yes. Yeah. These two are, let me look at it. The structure is trigonal bipyramidal. This is the central, for a general trigonal bipyramidal structure, there are 5 bonds, 3 in one plane and 2 above and below the plane of this trigonal. So hence the name trigonal bipyramidal. In one plane there is a trigonal triangle, and above and below the plane there are 2 other bonds which are connected to this plane, to this central atom. So it's a name trigonal bipyramidal. And these 3 are called as the equatorial bonds in the plane of the molecule where the angle is 120 degrees. And the 2 other bonds which are above and below the plane of this triangle are at 90 degrees to these equatorial bonds. So these 3 are called as equatorial bonds. And this one is called as an axial bonds. So there are totally 3 equatorial bonds and 1, 2, and 3 equatorial bonds and 2 axial bonds in this trigonal bipyramidal structure. And this axial bonds is little longer than compared to that of this equatorial bond. So this is what is about the trigonal bipyramidal structure, and everything is based on this equatorial and uh, axial positions. Now, coming back to this, the hybridization is sp3d, and its shape is the structure is trigonal bipyramidal structure, which is discussed. So, steric number is 5, which means that there are 5 positions around this central atom, around all of which 3 are bond pairs, which are connected to these 3 fluorine atoms, and 2 are lone pairs. So, now the question arises where these lone pairs are to be placed, whether they are to be placed at the axial positions or at the equatorial positions. So let's discuss that, where they are to be placed, and that completes the shape of the molecule. Yes, when we come to this, if you look at it, these lone pair of electrons can be placed either at the axial positions. See, these are the axial positions, and these 3 are the equatorial positions, 1, 2, and 3. So these, if 3 fluorine atoms are placed at equatorial positions, that means at the plane of the triangle, and the 2 lone pairs are to be placed at the axial positions. Or the other possibility is they can be placed one at equatorial position and the other at axial position, or they can be placed at the axial positions. The 2 lone pairs can be placed at the uh, it's equatorial positions. 2 equatorial, 2 axial, or 1 equatorial and 1 axial positions. So out of these 3 possibilities, which is the best possibility? Let's look at it. We know that the structure with the less repulsions will be more stable, so that is the most possible structure. So out of these A, B, and C, which do you think is the most stable structure? Yes, let's look at it. When you look at the A structure, the 2 lone pairs at the 2 axial positions. So we know that the angle in between this is 120, and the angle in between this axial position and towards this equatorial position is 90 degrees. So, and one more thing to be kept in mind is lone pair repulsions is more stronger than lone pair bond pair repulsions, which is more stronger than bond pair repulsions. So the and if the lone pairs are placed at the equatorial positions like this, they will be facing the 120 degrees angle. So 90 degrees repulsions are more stronger in this case when compared to that of this 120 degrees repulsions. So based on these two factors, that is 1 and 2, we should be able to say which of these 3 structures will be more stable. Yeah. Let's look at which of the structures is more stable. When we come to the structure A, so how many 90 degrees are repulsions are there? Let's look at it. So, with this lone pair, 1, 2, 3. 3 lone pair bond pair. And again with this lone pair, 1, 2, 3. So total 6 lone pair bond pair repulsions, that is of 90 degrees. And when I come to structure B, and one is placed at the axial position and the other at the equatorial position. So when we look at this, how many lone pair bond pair are there and how many lone pair are there? So one lone pair, because this is at 90 degrees and this is with this angle. So this is one lone pair lone pair repulsions and 3 lone pair bond pair. How? So when you look at this, this is at 90 degrees with these 2. So 1, 2. And again, when you come to this, there is a repulsion in between this and this. This is also 90 degrees. So total 3 lone pair bond pair repulsions. And when we come to structure 3 here, so how many repulsions are there? So these 2 are the lone pairs which are placed at equatorial positions, right? So 1, 2 with 90 degrees. These are the axial positions. And with again this one, 2. 1, 2. So total 4 lone pair bond pair repulsions, that is of 90 degrees. So this is also of 90 degrees. So Based on this, which do you think is more stable? This has 6 lone pair bond pair. This has also 4 repulsions, but one is lone pair lone pair. We know that lone pair repulsions are more stronger than any of the other kind of repulsions. So this is also ruled out. This has 6 lone pair bond pair. Only this has only 4 lone pair bond pair repulsions, which means that this is more stable structure. So according to the repulsions, this is the most stable structure out of the 3 possible structures for ClF3. So C is the, let me write it here, C is the most stable structure because of minimum repulsions, most possible structure because of minimum repulsion. Yes. So based on these two factors, that is the repulsions in between the lone pairs and bond pairs, and based on the angles at which they are placed, that is, we can decide which is the most stable structure. And according to this, the C structure is having less repulsions when compared to that of the other two structures. Therefore, C is the most stable structure, which is the possible structure for, yes, uh, ClF3. So we can come to the conclusion that, so this is the structure for ClF3, where Cl is the central atom, that is the chlorine, with 2 lone pairs at 2 equatorial positions and 3 fluorine atoms, 1 at equatorial and 2 at eggshell positions here. So when we look at this, we can say that if we can pass a common statement that if the lone pairs are present, that means 2 lone pairs are present in a trigonal bipyramidal structure, they are placed at the equatorial positions in order to minimize the repulsion. So when you look at this, just rotate it like this. So this Cl, F, 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 and 2 lone pairs placed here. So while looking at the shape of the molecule, I've already discussed that these 2 lone pairs are to be ignored. So this has the shape of a T here. So the ClF3 T-shaped structure, and if you see at the bond angle, what do you think is the bond angle? It is around 87.4 degrees. Yes. Yes. So the bond angle here is 4. This is because of the repulsion in between the lone pairs and these bond pairs. The bond angle is slightly reduced from 90 to 87.4. So we can come to the conclusion that ClF3 is T-shaped with a bond angle of 87.4, and the 2 lone pairs placed at the equatorial positions rather than at the axial positions, because this particular structure with the lone pairs at the equatorial positions is the most stable because of the minimum repulsive forces. So this is the structure of ClF3, and there are other structures, I mean the shapes of the molecules also discussed in my YouTube channel, which have been uploaded on my channel, which has been given in the description box below. So if you like it, please do like, share, and subscribe my channel. Yes.